Good afternoon, students. Today we are going to discuss in this session uh, a Picosecond Electro optic sampling, which comes under that is a Unit 5. It is a technique, a new technique, evolving technique. So here three kind of applications discussed here in this topic, but still evolving. So that we are discussing here. The electro-optic sampling technique is a new characterization technique based on short optical pulses and the electro-optic effect. We use the two things by means of short optical pulses and the electro-optic effect. Here the short optical pulses are in picosecond or femtosecond that are used for characterizing the signals. With this signals means here is electrical signals. With this technique, electrical waveforms have been characterized with a temporal resolution of less than 300 femtosecond, corresponding to a 1 terahertz bandwidth. The electro-optic sampling was first used to study the dispersion of picosecond electrical pulses on transmission lines. This is actually the first application of electro-optical sampling. So in order to study the dispersion characteristics in of a picosecond electrical pulses in a transmission line, this is the actual the need of a first. Using a superconducting transmission line, it has been recently shown that conduction losses can be defeated and the single picosecond pulse is propagated over a few millimeters. So the recent development. Additionally, ultra-fast transistors have been tested with a single picosecond resolution. That is, the transistor response was time resolved as the gate was pulsed using a step function with a picosecond rise time. Here, three things: MESFET, TEG-FET, and preamble. That is PBT, permeable base transistors. So their responses have been studied by means of this evolving technique, sampling technique, electro-optic sampling technique. And here we use the switching times as low as noted. And the switching times as low as 5 picosecond have been directly measured for the BBT. That is permeable base transistors. Because gallium arsenide exhibits the Pockel's effect. Because of that Pockel's effect, we can the components, GA's components and the circuits can be directly probed in a non-invasive way. So with this an introduction, we go for that. So important to know that as the switching speed of microelectronic circuit increases, so many problems arise in characterizing the real-time responses of these circuits. When you go for measuring the characteristics of microelectronic circuits, If the switching beats is high, then definitely there will be a raising of many problems. So that we need a new technique, that is a faster technique for measuring the microelectronic circuits responses, characteristic responses. So that we go for a new technique. That is, this is actual technique what we are today we are discussing here. This technique is a typical for a new device to be faster than conventional electronic techniques that measures the responses of microelectronic circuits, even though they are having high switching speeds. That is the thing we have to note it. So here see this figure 1a, here you see the figure which illustrates the evolution of the sampling system for characterization of fast transients over the years. The first technique is based on the tunnel diode and was introduced by electronics in the late 1960s. Using Josephson junctions and cryo-electronics affairs, that is reported in Paris and Wolf. Signals could be sampled with 2 picosecond gating time. With advances in ultrasound laser pulses, new techniques were developed using laser-induced photoconductivity. It is reported in another paper, and the electro-optic effect is used again with photoconductivity, laser-induced photoconductivity for electro-optic sampling. Actually, in our discussion, we are taking this one, the electro-optic sampling, with its few terahertz potential bandwidth. This is we are giving importance to study the technique, electro-optic technique, sampling technique with a potential of a few terahertz. Now we come for that detail of this technique. This electro-optic sampling technique is based on, as I already said, short optical pulses. Short optical pulses means the duration may be femtosecond or picosecond. And this technique based on short optical pulses as well electro-optic effect, that is induced by refringence in a non-centrosymmetric crystal by signal under analysis. So we are taking this. The signal undergoes in the non-symmetric crystal. Then the electro-optic sampling technique is very useful for sampling purpose in the induced birefringence of a non-centrosymmetrical crystal signal propagation studies. Here in the second figure 1b, here noted as 1b, exhibits the general explanation of the technique. This experiment, the demonstration for electro-optic sampling, demonstrates excellent temporal resolution to down to several hundred femtoseconds. Because of extremely short pulses, down to 30 femtosecond have been here it is demonstrated. But the speed limitation of this technique, because of the lattice absorption appearing in the terahertz range, it is actually this is a limitation. According to the material what you are using, in our electro-optic sampling technique. So another thing is the sensitivity is in the order of 50 microvolt per square root of the hertz. A typical waveform produced by a photoconductive switch triggered by 100 femtosecond pulse is shown in figure 2. Here you see this in figure 2. A high repetition rate, that is approximately 100 megahertz. So here from the general configuration electro-optic sampling system, you may understand here for explaining this how it works. The high repetition rate, approximately 100 megahertz strain of picosecond pulses, is split into a trigger beam and a sampling beam. First, the trigger beam initiates the generation of the electric signal to be characterized, which propagates through an electro-optic medium. And the next one, the sampling. Actually, what we had to do before sampling, then we need a beam of electric signal that is should be generated by the trigger beam. Here in this demonstrations is given. The sampling beam travels through a scanning delay line and then through the focal cell modulator arrangement. The intensity of the sampling beam is measured by a lock-in amplifier and then plotted as a function of delay, that is characteristics of the signal plotted as a function of delay. What you have, the resulting in an equivalent time representation of a picosecond electrical signal. And the early work all performed on the balanced strip lines, the electro-optic technique has been adapted to a wide variety of measurement situations. For doing this, many different examples of our electro-optic modulations have produced. We say for that is a world. Figure 3 here depicts a simple cross-sectional views of 6 different modulator configurations that each utilizes some form of traveling wave electrode geometry either on the electro-optic crystal itself or in the circuit being measured. Both are reported in Koellner et al. Here you see in this figure, you may see a typical waveform produced by a photoconductive switch is captured using electro-optic sampling. Its temporal resolution is less than 300 femtosecond. So in this figure, the various examples of electro-optic modulators are shown. One is the transverse balanced line modulator, the other one is a coplanar line modulator, transverse line geometry, then third one coplanar line modulator, longitudinal backside sampling geometry for use of non-invasive integrated circuit sampling, where the substrate is also electro-optic. Longitudinal microstrip modulator, which has also been implemented for non-invasive sampling of integrated circuits. The figure D shows a transverse superstrate moderator. And figure E, horizontal electrode less probe modulator. Then figure F, vertical source electrical electrode less probe modulator. So here you see this, the shaded areas are representing electronic device substrates, whereas that means typically a semiconductor, while the clear areas represent dielectric, that means electro-optic media. So now we come for one example. That is here the electro-optic sampling is, as I already said, the three kind of applications are listed there. In first, we take one example, that is for studying the dispersive characteristics of a transmission line. So first we start with the transmission line placed at room temperature. This demonstration is reported in a paper Valdemanis et al. So here we come for discussing the electrical dispersion in strip line electrodes. The dispersive effects in the open transmission line electrode geometry can be considerable for high frequency signals. Dispersion is due to frequency dependent relative effective dielectric constant E epsilon effective and the specific electrode geometry. This is in typical microstrip electrode geometrics, there exists a critical frequency Fc at which the onset of a significant dispersive effect appears. Due to the excitation of spurious modes in the form of surface wave Tm and Te modes, the critical frequency at which coupling occurs due to the fundamental quasi Tm mode is given by Fc equal to V naught by 4h into square root of effective dielectric constant E relative effective dielectric constant minus 1. Here V naught is the velocity of light in vacuum and H is the electrode separation. The critical frequency occurs in the regime where the electrical wavelength in the dielectric is of physical dimensions comparable to the transmission line cross-sectional dimensions. So in this regime, so we impart our discussion below the critical frequency, and that is here E effective epsilon effective assumes a constant non-dispersive lower value, that is termed as epsilon Tem, and the above critical frequency is equal to a higher relative dielectric constant epsilon relative, and just here you see that below the critical frequency we termed as Etm epsilon Tem, and higher above the critical frequency we termed as this is equivalent to relative dielectric constant E epsilon Rel here. So continuously the E effect will be changing. This the epsilon relative is also a non-dispersive, considered here. All the values E effective, epsilon Tem, epsilon Rel, all are non-dispersive dielectric constants. Hence, so we have to take it carefully. Hence, the dispersion curve is basically two-valued with a smooth transition regime in between. The electro-optic sampling system provides a unique method, as reported early meanings, of measuring these dispersive effects in an electrical signal as it propagates along the transmission line. So actually this method used for that. First, by translating the sampling beam by a known amount with respect to the stationary modulator, it is possible to interrogate the modulator aperture at ever increasing distance from the electrical signal source. This configuration is depicted given in this figure. Sampling at each successive point provides progressive pulse shapes that displays the accumulating effects of the dispersive stripe line on the electric pulse. Here you may see the photoconductor detector as it propagates along a 250 micrometer thick modulator as it's shown in the figure. Here you see this in this configuration. When a signal contains frequencies in the regime of the critical frequency for a particular geometry, as in this case, the dispersive characteristics of the strip line conceptually divided the signal bandwidth into two pockets. That is, pocket 1 containing the lower frequencies, the pocket 2 containing the other higher frequencies. The lower frequencies will experience a lower effective dielectric constant, and therefore it travels, the packet 1 travels at a higher velocity along the strip line, whereas the packet 1 travels more slowly due to its increased dielectric constant, effective constant. So that the higher frequencies are traveling in a high speed, very slow speed. Thus, as the pulse propagates, its higher frequency components appear later in the waveform. Figure 5 illustrates the effect of a dispersion produced on picosecond electric pulse at different points along a 250 micrometer thick balanced microstrip transmission line. Now we compare the dispersive characteristic study. From equation when already we given this, it can we see that the dispersive characteristics of microstrip transmission line are sensitive, that is highly proportional to the product of the electrode separation and the square root of the substrate dielectric constant. Here you see this in figure 6a, compares the magnitude of the dispersion for several different stripe line electrode geometries by plotting the rise time of the test pulse as a function of a propagation distance along the stripe line. Here you see in the figure 6, curve A, 6A, you see this, the left side figure, 6 in 6A, figure 6A, there is a curve that is termed as A, curve A. It plots the rise times of a pulse traveling along 500 micrometer thick balanced transmission line on a lithium titanium oxide with epsilon, relative epsilon coefficient, that is dielectric constant coefficient equal to 43. The significant dispersion is observed because of relatively a large electrode separations and high dielectric constant. To decrease the electrode separation, another researcher used a coplanar line on lithium LiTaO3 surface. Here you see this curve B in figure 6A. Curve B plots the dispersion of such line with a 50 micrometer electrode separations. As predicted, there is a noticeable improvement over the balanced line geometry. Recently, that is 2010, recently the Karaikudi et al. Have implemented a similar example demonstration of this electro-optic sampling technique to study and successfully develop a new transmission lines that can propagate picosecond electrical signals with less dispersion than has been previously what we have used in this discussion itself. Their design, their experiment is an air-spaced microscopic geometry where the upper electrode is supported by 125 micrometer thick glass superstrate 500 micrometer above the ground plane. The electrode width is 750 micrometer. Measurements were done by sampling a small piece of LiTaO3 inserted into the electrode air gap. Due to the elimination of high dielectric between the electrodes, the electric field exists predominantly in the uniform air gap, thus significantly reducing dispersion. Again, you see the figure 6a. Here, the curve C shows the improvement of nearly 2 orders of magnitude of a previous curve A and curve B. In curve D reports the superconducting transmission lines. So, from that you can understand how it is the sampling techniques evolving and producing thing as there. Then after that, here two things are discussed. The same technique used, electric optic techniques used here. Now another for superconducting transmission lines. And first thing is in a room temperature. The transmission lines placed in the room temperature, but here the transmission lines placed in superconducting environment. So here in this figure, the experiment and as well the performances are this sampling reported. Then so as we said, the third application of this method, this technique, so we go for the characterization of high-speed transistors. It is reported in the MOSFET or TECFET characterization is reported here. From the characteristics curve, we can understand the improvement of sampling schemes, what you discussed in this there. The another here we use this technique, electro optic sampling technique, femtosecond, picosecond electro optic signal is in PBT transistor for characterization of this one, that is a permeable base transistor. It is reported here, and the experiment as well in the characterization also the response of the sampling, effectiveness of the sampling also repeated here. Now we come for concluding this session, that is here the electro-optic sampling. In this discussion, presently the best technique is to look the waveform, to cut waveforms in a non-invasive way with a few hundred femtosecond resolutions. This technique has been used to study the response of circuits and devices with unprecedented resolution. And this technique play a key role in helping the electronics to move from the gigahertz to the sub-terahertz region. So with this I conclude the femtosecond electro-optic sampling technique. Thank you so much.